would be 270 dBs is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 dB in Earth's atmosphere, as different mediums have different volume caps due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the sun would be 100 million times higher than this cap. The sun is loud, which is a shame, as some of the sun's sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the sun has reached us, many of the sun's sounds have blurred into one meaning. We miss out on some of their fascinating intricacies. To gain a better insight into the sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the sun for now, and instead let's focus on its sound patterns. If we were to enter a spacecraft and head towards the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas. To date, you see, it's tempting to think of this stream from starting inside the sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, important discovery had been made through observation. Although particles within the sun's atmosphere or corona were moving around with an average speed of 145 millibars particles outside of the corona, were traveling at 618 millibars. This meant that particles that had enough speed to escape from the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma, too. It is far too hot, although you might expect the center of the sun to be the warmest part of it, and the temperature to gradually go down the further from the center. This stops being true once you enter the corona. The surface of the sun has an average temperature of 5,600 degrees. But within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees. Something in the sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It's here that we would meet the third sound of our tour of the sun as our spaceship would draw closer, and we passed over the boundary between the corona and empty space, something known in S as the Alphen surface. We would begin to hear the music following these are known as Luer waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, a magnetic equivalent to the sound a kettle makes when it boils. We have entered one such dream. Countless of these streams fire out from the sun's surface. The sun's exterior is covered in islands of hot material rising from the stars. Once there, the material cools and sinks back into the star's mass along the island's edge. And something about this process of rising and falling material, or something going on within the sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped up by the magnetic force and is sent streaming into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Luer waves is eerily beautiful as the winds head out. Not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds as faster parts of the wave run ahead, while slower parts of the wave fall behind, creating what are known as dispersive music waves. Such waves are filled with churs, little eddies of sound, where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this evens out into the hum. We heard at the beginning, there is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications here. Right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth whenever lightning cracks. You get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away. If you have the right detectors to truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles. Nothing too special now. Here's what they sound like on the music sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the sun's magnetosphere is not just experiencing the odd crack of lightning. Something is going on constantly all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that draw is being caused by. But at least one theory for the force behind the sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Magnetic reconnection sounds fairly innocent, and yet its innocent technical-sounding name disguises a cataclysm. The sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart I cannot stress.